let's get started. Let's get it. You guys ready? Can I get a thumbs up from you guys or like a camera on, like from you guys?
I'm wrong.
If you guys are like ready, just let me know that you guys are
Frankie.
ready. Yeah. All right. All right. Frankie, you all right, man? You look like you're walking over there.
Yeah, I'm good. I'm just turning on the light.
Oh, gotcha. All right. Cool. All right. This is it. This is our last lecture. I know some of you are getting a little emotional. I know I am a little bit here. Today we are pretty much going to be finishing up McLaurin and Taylor. Not really much to finish up here, and doing some examples so you guys are ready for this final tomorrow. A couple of things about tomorrow. So I kind of wanted to, open it up to everyone here. Your final tomorrow is at 9:50. Would you guys want me to like be on Zoom early so that you guys can like ask your last minute questions and things like that? And then the next question is, well, how early do I need to wake up?
Early is too early for you.
There's no limit. Let me know ahead of time. And,
there is no limit. The limit does not exist.
The limit does not exist. Yeah.
Are you sure about that? Because
I mean, I'm not gonna wake up at like 5 a.m. for you guys. I mean, that's too much. I don't think you guys do you guys know how to wake up at 5
We're not even gonna be.
Yeah. I don't think you guys know how to do that. So.
No, we would still be awake by then, so there's no waking up needed.
Oh,
exactly.
Because you guys gonna study into the night. Yeah.
Yeah.
Obviously.
That's typical college behavior, you know. No, seriously, please get some sleep. 2 hours of math, especially if your brain's not used to it, your brain will get fried. And you have another exam that day too, so keep that in mind.
Oh, word.
Yeah, writing.
Yes.
Wait.
Okay, so I don't know. I'm gonna throw a number out there, and I'm gonna see what you guys say. How's 9 o'clock? Is that not enough time? Is that too early?
That's good.
9 sounds.
Do you want anyone want 8:30? I can do 8:30. It's fine. I will have like bags under my eyes though, so just when you guys.
I think 9 would be good.
Are you sure?
Yeah.
Anyone else it's open to everyone.
What time do you usually wake up?
I'm just messing around. I wake up at like around 7. Like I'm an adult. I know how to wake up on time.
I'm an adult.
But I know you guys are used to waking up later in the day, so freaking teenagers. So 9 o'clock?
Yeah.
So 9 o'clock is okay. Okay, so it's been decided. 9 o'clock.
45?
I'm going to open up the Zoom thing at 9 o'clock. Come early. Even if you don't want to come in and ask questions, do not come at 9:50 because 9:50 is when the test starts. So come at least 10 minutes early, 10 to 20 minutes early. Okay? And that's honestly, that's my recommendation for like college. Like, once we get out of here, once this quarantine's over and like college becomes normal again, going to your lectures and stuff, you shouldn't get there at the time that it starts. You get there at like at least 10 minutes before. Yeah. All right? Especially if you're taking a bus or whatever, like if you got to walk there or whatever, you got to start thinking ahead. All right? What's up, Lamek?
Start at 8:50 instead of 9. That feel like it's like that perfect hour and everything.
Sure, yeah. I'll be there at 8:50. Okay, so 8:50. Make sure you submit this thing on time, all right? I really hope you guys don't screw up the submission thing. And oh my gosh, follow the directions. I'm surprised I have to say this. There were a handful of you that kind of messed up on quiz 2 and 3 just because you didn't read the directions. Some of you were giving me answers that I didn't even ask you about that kind of stuff, so it's like, make sure you read the directions carefully. Like if it asks you, does the series converge or diverge? Okay, you got to say, that it converges or diverges and with proper justification. If the question gives you a sequence, that is a different type of question. You got to pay attention to that, right? A lot of people, they thought the sequence questions were series questions, and then they lost a lot of points because of it. All right, so this final, it will have sequences and series on it. So So make sure you know the difference, right? And then power series. Make sure you know the difference between a power series and a regular series, right? So you guys have to pay attention to the directions, all right? During the final, feel free to ask me like, oh, John, did you mean like XYZ on this, or like, did you mean that this was a suit? Like, I can tell you, I can help you with that, all right? I think that's pretty much it. Let me finish up the Taylor and Maclaurin series stuff first, and then we'll review for the final. Okay, I'll go through like the topics that are on there and all that stuff. All right, sound good? All right,
Yeah.
let's do this thing. So last class, I think we came up with this formula. And this was for
Oh yeah, you would.
this was for Maclaurin's series. Okay, and anyone want to remind me what makes something Maclaurin?
If it's centered there.
Yeah, so Maclaurin series means centered at sometimes you'll see C, sometimes you'll see A, but just know that means like it's referring to the center. Okay, and then we also talked about the 7 deadly series, right?
Mm-hmm.
So let me just rewrite them here. Deadly series. So they were, the first one was 1/1 minus x. So once again, function, the sum, and the interval of convergence. So 1/1 minus x, and this one looked like x to the n from -1 to 1. Second one was 1/1 plus x, and this one just had an alternator. I'm just rushing. That's why I'm ignoring the indexes. The third one was tan inverse of x. And this was, there's an alternator. There's x to the 2n plus 1 over 2n plus 1. Ooh, help me out here. What was the interval of convergence? Did any one of these, no, they both converge, right?
Yeah.
Yeah. Fourth one was ln of 1 plus x, which is, this one was tricky. It was like that, and like it was x to the n over n or something. I think like it started at 1, and then this one only converges at 1. No, yeah, right? Yep. I think it only converged at 1. Oops.
Yeah, it only converges at 1.
Thank you. And then the last 3 were sine, cosine, and e. So sine, cosine, and e. So sine was like, there's an alternator. So, a really, really neat way to memorize the sine and cosine one, all right? If you guys remember, sine is an odd function. Do you guys remember what that means?
Yeah.
It's reflective
It's
about y equals x. Cosine is an even function, right? So a really easy way to memorize this is sine is going to be x to the odd over odd factorial. Do you guys remember me talking about like odd and even with these numbers, right? This converges everywhere. Since cosine is even, it's going to be x to the 2n over 2n quantity factorial. This also converges everywhere. And e to the x is no alternator. It's just x to the n over n factorial. I think they're all 0 to infinity except ln. And this also converges everywhere. I wanted to actually show you guys something today with this whole converges everywhere and like kind of what it means in terms of the graph. All right, so I'm going to look at sine of, I'm going to look at sine of x. Okay, you guys can see that, right? All right. So here's sine of x. Yay! I know it. You should know what that is, right? Like you should know amplitude of 1, yada yada yada, right? So this is what I did. I prepared some terms from the sine of x function, the series, sine of x series. All right. The first term in sine of x is just x, right? If I plug in 0 into the formula, it's going to spit out an x. So watch. Okay, it does that. And you're like, all right, it's not that really impressive, right? But you do see that, like, if I get closer and closer to the center, right, it is a very good approximation, right? Make sense?
Yeah.
And just think about it, that's just one term. All right, well, what if I added another term? Ready? Huh, look at that, right? It's a cubic function and it kind of fits pretty well, right? And then it starts to like be a bad approximation like as you get further from the center, right? And this shouldn't be new news. And then I add a next term and you're like, oh snap, that's pretty close. That's pretty good. This is a pretty good approximation, right? And I add another term and you're like, huh, it's getting there, you know, like it's actually like right on top of each other, like from the center like outwards, right? And then I went out to like, I don't know how many terms is that. I don't know, that many terms.
19.
It's not 19 terms, right? Because it's only the odd terms, so it's like half of 19,
Oh, yeah.
which is like 8 or 9 or 10 or whatever.
Yeah.
So I went out to that many terms, and look at that. It's like almost perfect. Do you see that? So like, as I keep adding on these terms, right? If I were to add on another one, so oh crap, can I undo that? Oh, thank God. All right. So if I were to add on a one after that, right? So it's going to be plus x to the 21 over 21 factorial. It took a second there, but yeah, you see, it became an even better approximation. So this is what converges everywhere looks like. It doesn't matter what x value it is, right? It's going, as long as the series keeps going out to infinity, it's going to keep like getting closer and closer to sine of x. Yeah, make sense? Anyone have any questions about that? Great. So that's the 7 deadly series. I'm not going to require you to memorize them, but they will in the fall. They will probably, these are very, very common Maclaurin series. So you have to know how to kind of play with them and manipulate them. There's a section in this part of the chapter where they're like, if we know Maclaurin series, then we know we can like kind of I don't know how to explain. It's like treat them like parent functions. You know what I mean? Like if I had a parent function and like I gave you some shifts, you should be able to tell me like what it looks like and stuff like that, right? Well, with these, if you're given something like that resembles a deadly series, then you should be able to tell me what the Maclaurin series is. You know what I mean? So if I said this centered at a equals 0, so it's Maclaurin, right? Then what this means is like all I have to do is multiply x to the e to the x representation. You get what I'm saying? Like we found out that this is the sum from n equals 0 to infinity x to the n over n factorial. Well, if that's the case, then I know that this function is going to be x times all the terms in e to the x. So what that means is it's just, I need to use my exponent rules, right? This just becomes n equals 0 to infinity of x to the n plus 1 over n factorial. And that's it. That's centered at 0, and that represents the given function. Do you see what I'm saying? It's kind of like when I made the jump from like 1 over 1 minus x to like, I don't know, 1 over 1 plus x squared, right? You can identify the parent series, I guess I'll call it, right? And just make like a quick substitution. All right. This really isn't going to be on the final, but it will show up a lot in the fall. Okay. I feel like I say that so much. So I'm going to just leave that. Like if you want to look more into that, that is on page 622 PDF. It's the PDF page. So page 622, example like 4 and 5 and I guess kind of 6. It's just like these are like tricks to like shortcut ways to find series representations of functions. All right. But I'm just going to show you guys the long way for today, and I want you guys to do that for for the final. Is that all right?
Yeah.
Yes. So these are, I guess I can call these like the shortcut ways. I don't know. Excuse me. So yeah, let's do one. Let's do a real one. I practiced this before today's lecture. So, and I was like really getting into it. It's good. All right. So we're looking at, this is example 1 on page 620. It says find the Taylor series for f of x is equal to x to negative 3 centered at x equal, oh, I'm sorry, c equals 1. Okay. Wait, did I explain what a Taylor series was yet? No, I don't think I did, right? Oh, shoot, I'm sorry. I'm doing the example before I explain the thing. Okay, it's really easy. It sounds really complicated, but the only difference between Taylor and Maclaurin is just the center, okay? Maclaurin series are much more easier to play with because they're centered at 0. And if you think about it, like I'm plugging in zeros, it's like things will like go away and stuff like that. With Taylor series, the center is not at 0, which means your camera, right? Remember how I said that this is kind of like you're looking at like a section of the function, right? Your camera, you're just moving your camera to a different part of the function. So if my center was at 4, that means I'm moving from 0 to 4. Did I move in the right direction for your screens? I don't know. I hope I did. But I'm moving from 0 to like x equals 4 and looking around that general vicinity. Does that make sense?
Yeah.
Yeah. Okay. So in this case, for this problem, I'm moving from the center of 0 to the center of 1. So I'm not looking at, you know, the function values at 0 anymore. I'm looking at the function values near 1. Okay. And the only difference, man, this guy does not want to stop calling me. The only difference in the formula is that instead of plugging in 0, you're plugging in the center. So the formula looks like, it's going to look almost the same, right? A is the center over n factorial. And then we now have to include this shift by doing that. And that's the formula for Taylor series, right? You guys can see this looks exactly like the Maclaurin series. It's just instead of 0, there's an A. Is there any confusion on that whatsoever? Please be honest. John, can you say that again? I kind of missed it. No?
John, this kind of relates back to like the power series, like how there was an x minus a.
Yeah. Sort of. Yeah. It's just instead of like seeing that, right? Instead of the c sub n, we kind of redefine the c sub n using the given function, right? We did that all last class, which I'm pretty sure I lost like all of you on that part, but whatever. It's on there. It's in the video, so if you're interested. So okay, so we're gonna use this formula and figure out what the series representation of x to the negative 3 is centered at 1. Wow, that's a mouthful. So here we go. Ready? When doing this, like kind of like the long way, try your best to stay organized. Okay. There's going to be things that we're going to need. So first, we're going to need the functions, right? Like the functions and their derivatives, right? So we're going to need
John, Siobhan said,
Done. Yeah.
there's something in the chat. I don't want to cut you off, but he said, "Can you repeat what you said before?"
Repeat what? Difference between Taylor and Maclaurin? Repeat what? Okay, so once again, Maclaurin, like all these 7 deadly series that I just wrote down here, right? These are all centered at x equals 0, right? Like if you think about it, all of these x's, you can technically write it like that, right? My center is 0. So for these 7 deadly series, all of them are centered at 0, meaning the camera is focused at x equals 0 for the function. But as soon as you start pulling away from 0, right, changing the center, that means you're looking at a different part of the function. So that's what Taylor series are. It's just when you're not looking at 0, you're looking at some other part of the function. Did that clear it up, Juma? Okay, I'm just gonna move on. Okay, all right, cool. All right, so when doing this, right? So looking at this formula, okay, just think about it. This part pretty much stays the same. This part pretty much stays the same, right? All you're doing is writing out, 0 factorial, 1 factorial, 2 factorial, and so on and so forth, right? And then for the x minus a, in this case, it's going to be x minus 1 to the 0, x minus 1 to the 1, x minus 2, so on and so forth, right? So I feel like the hardest part of this is this, figuring out the pattern, and then kind of like, canceling out anything you need to cancel out, right? So here we go. Let's do our best to stay organized here, okay? Especially some of you, one, either need to work on your handwriting, or two, need to not cram everything in one paper. Like, you don't get a prize for that. I'm just letting you know, you don't get a prize for fitting all of your work into one paper. Please, space out your work, it makes my job a lot easier. I don't have to do this as much, when I'm grading. So please, space out your work, take your time, writing your thoughts down, right? Anyways, so we're gonna need one, I guess, column for our function and its derivatives, right? And then we're gonna need to plug in our centers, right? Because that's what, come on, okay, that's what this part is. We're gonna have to plug in 1 into all of these, right? So this is gonna be f of 1, f prime of 1, f double prime of 1, f triple prime of 1, and so on and so forth, right? So here we go. The function is x to the negative 3, or 1 over x cubed, right? Whatever you like. Now, when I derive this, I get negative 3x to the negative 4. Okay? Negative 3 times x to the negative 4, right? Hopefully you guys didn't forget how to derive.
Mm-hmm.
And at this juncture, for me, I'm I think I see a pattern, but I'm not 100% sure what the pattern is. So if that's you, that's fine. You're just like me. Derive it a couple more times until you start to see something going on, right? For me, one is definitely not enough for me to see, right? So I'm going to derive this again. And then I'm going to do, so when I derive this, it becomes positive 3 times 4, x to the negative 5. And I'm like, something happened here. It looks like it's starting to alternate, right? The 0th derivative, which is just the function, is positive, and then it became negative, and then it became positive. My guess is the next one's going to be negative. And it is, right? It becomes 3 times 4 times 5, x to the negative 6, all right? So hopefully at this point, you kind of see it maybe, all right? But let's start plugging these in and see what we get here. So I plug 1 into the 0th derivative, right? So this is when n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3, right? So this becomes 1. When I plug it into the next one, I get negative 3. When I plug it into the next one, I get 3 times 4. Now, there's a reason why I'm writing it like that and I didn't write 12. Can anyone tell me? Why did I write it as 3 times 4 instead of 12?
You could recognize the pattern easier.
Yeah.
Yeah, with a lot of these, there's probably, most likely there's going to be a factorial that starts to emerge, right? Think about it. If I'm deriving, right, a power comes down, and then derive the next one, a small, I guess in this case, a bigger power comes down. So yeah, I'm going to leave it as 3 times 4. This one becomes negative 3 times 4 times 5. Any questions so far? Am I going too fast? John, where did the 3 times 4 times 5 come from? No? No? I'm just plugging in 1 in for x. That's it, right? 1 to any power is just 1. So those just end up going away. All right. What are we doing here? You know what? I'll do one more without even taking the derivative. Watch, I know, it's like magic, right? So 4th derivative at 1. I'm just going to take a guess here. It's going to be positive because I'm just looking at the pattern. There's going to be a 3, a 4, a 5, and a 6. Do you guys believe me? Do I need to explain that? No, right? Okay, good. So watch. Now that we have a couple of these terms, I'm going to use the formula. I'll rewrite the formula here. I should have, yeah, whatever, it's too late. So the formula, once again, okay, I'm going to plug in the values from this problem now. It's going to be nth derivative at 1, because that's our center, over n factorial times x minus 1 to the n, because our center is 1. So far, so good? Anyone lost? It's okay. You can say, this, John, I have no idea what's going on, because that was me when I was taking Calc 2. I was like, every time I saw this, I was like, I don't know what that is. If that's you, speak now or forever hold your peace. Not forever. Okay, fine. Just message me if you're confused. Okay, so this is what we're doing. We just found all of these values, right? All of those values represent that guy, this numerator. Yeah? So this is what we're going to do. We're going to string out the first 4 or 5 terms and see what's happening, right? So watch. This is equal to, so the 0th derivative, once again, 0th derivative just means you didn't derive it, right? So it just means what happens when you plug 1 into the function. Well, we got 1, if I remember correctly, right? We got 1 over 0 factorial times x minus 1 to the 0. Is that bad? No? This is the n equals 0 term, right? Okay, plus, now we're going to do the n equals 1 term. So that means the first derivative at 1. And we got -3. Yeah? So I'm going to plug in -3 over 1 factorial, x minus 1 to the 1. This is the, oh, come on. This is the n equals 1 term. Anyone lost yet? Okay, I'm taking this super slow for, because I want you guys to see what's going on. All right, so now we do the next one. Help me out here. What was the second derivative at
John, check
3
the chat.
times 4. Yeah.
Shuban, how is it -3? We plugged 1. I was on this line. We plugged 1 into our first derivative. And it becomes -3. Okay, good, awesome. Guys, ask your questions, please. Ask your questions. So now we need the second derivative at 1, which is, anyone? I can't see, it got cut off.
3 times
3
4.
times 4.
3 times
3
4
times 4
over
thank
2
you.
factorial.
Over 2 factorial, thank you. Thank you. All right, and so we just keep on going. We keep on going. Let's go until we get all our terms here. This becomes plus -3 times 4 times 5 over 3 factorial x minus 1 cubed. Come on. And then plus 3 times 4 times 5 times 6 over 4 factorial x minus 1 to the 4th. Okay, so from here, it's kind of confusing, right? It looks a little like, oh man, I have to kind of figure out the pattern, right? Well, let's figure out what we know, right? If I wanted to write this as a general term, well, what do we know for sure? Like, what can we just write down?
That it's alternating, so you could
okay, yeah, sure. Yeah, it's alternating, so we need an alternator. The first term is positive, so I'm going to say that's a 0. So I'm going to say -1 to the n. So good, that's a good place to start. It's alternating. So the sign's taken care of. I can lock that away. What else is the same in almost every one of them?
the over n factorial.
Um. Okay, fine. I guess we could do that. Sure.
They all have an x minus 1.
That's the one I was. You know what? I'm just gonna. Yeah, that's the one I was saying. So they all have an x minus 1 to the n. So now we got to figure out this middle piece, right? Like what's going on with this, with this, with this, with this, and with that. Okay. So this is the part that's probably the hardest part of the problem. Okay. Figuring out how to represent this generally, right? As a series. So let's think about it. Right. Well, on the first one doesn't really tell us that much, right? It's just 1 over 1 because 0 factorial is 1. So that's just 1. But then the second term, it looks like it jumps to 3, right? 3 and then over 1 factorial. And then the one after that, it looks like it's starting to become a factorial, right? It goes from 3 to 3 times 4. Does that make sense? And then it goes to 3 times 4 times 5, and then 3 times 4 times 5 times 6, and so on and so forth. So the idea is like, I need a factorial, but the factorial needs to eliminate what? What numbers are not being factorialed in this pattern in the top part?
2 and 1.
2 and 1.
2.
Do you guys see that? 2 and 1 are not there. So how do we eliminate part of a product but keep like the rest of it? Any thoughts?
By dividing it by another factorial that's under 3.
Yes, divided by another factorial. Does that make sense? Right? Think about it. If I have like n factorial, right? And then I divide it by like 4 factorial, what is that going to do?
Take out the first 4 terms.
I guess, it depends on what direction you're looking at it, but it takes out 4, 3, 2, 1, right? In this case, we only want to take out 2 and 1, right? Yes? You guys still with me?
So
I know, this is a little complicated.
You have to put it over 2 factorial.
So we need it, so it's going to become like something like over 2 factorial, but then I said it jumps, right? It jumps from 1 to 3. So what does that mean? Like, okay, when I plug the index of 0 in, it needs to spit out 1, right? Because that's what that is. And then when I plug in the index 1, it needs to spit out 3. So how do I do that? How do I make it spit out a 3 when I plug in 1?
You multiply it by 3.
Nope.
Okay.
Is it setting it to a power?
Would you do like n minus 2 or n minus 1?
Not minus. How do I go from 1 to 3? What?
You add 2?
Yeah,
2.
you're adding 2.
So then it would be plus 2?
No? Was that too much?
That.
I know. This is pretty complicated, but think about it, right? If I plug in 0 into that, what happens? I get 2 factorial over 2 factorial. There's that 1, right? There's this 1. Okay, I plug in 1. I get 3 factorial over 2 factorial. So you see how the 2 factorial on the bottom is eliminating the 2 and the 1, like we wanted. Then I plug in 2. I get 4 factorial over 2 factorial, leaving me with 3 times 4. Do you see that? Do you guys see that? I know this is kind of tricky, right?
Yeah.
You guys aren't used to playing with factorials. That's normal. All right, do we have any questions on this?
Wait, John. So it's n plus 2 factorial over 2. So you plug in
2
1.
factorial, which is, I guess, 2, yeah.
Yeah, so you plug in 0, and you get 2 factorial over 2 factorial, which is just 1.
Which is 1, which is this now black in the circle, yes.
Yeah. And then if you plug in 1, it's 3 factorial over 2 factorial. But what about the 1 factorial? That's what's kind of mixing me up.
Well, 1 factorial is just 1, right? 1 times 1 is...
Yeah, but is what we have here, like the n plus 2 factorial over the 2 factorial, isn't it supposed to represent what's in there?
This represents the
just the top
numerator.
Oh.
Yeah. I'm getting to the denominator in a second.
Okay.
Yeah. All right. So this essentially what we just figured out was this was the nth derivative at 1. That's this part. It's going to be n plus 2 factorial over 2 factorial and then with an alternator, which we already accounted for. But this thing that we just figured out, we're plugging all of that into the top part, right?
Yeah.
Like of our generalized formula. Like we just solved for that.
Got you.
Right? So we can't forget about the n factorial that's on the bottom. So this now becomes n plus 2 factorial over 2 over n factorial. And we can simplify this, right? Things are going to simplify because I have a factorial on top and a factorial that's, well, I guess going to be on the bottom. This becomes n equals 0 to infinity, negative 1 to the n plus 2 factorial time over n factorial, and there's a 2 on the bottom. X minus 1 to the n. And this finally becomes, right? If I have an n plus 2 factorial on top and an n factorial on the bottom, what terms are going to be left? I'll write it out. N plus 2 times n plus 1 times n minus 1 all over n factorial. Oh, sorry, n times n minus 1 times n minus 2. And what terms are going to be left after I cancel everything out?
Wait, isn't 2 supposed to be a factorial?
Well, 2 factorial is 2, right? Because 2 times 1 is 2.
Oh, okay.
Yeah.
N plus 2 and n plus 1.
Yeah. These are all going to cancel out, leaving you with the alternator, n plus 2, n plus 1, x minus 1 to the n. We did it!
Oh, John, I just have one question.
Yeah.
Where did you get the 2n factorial?
Oh, I'm sorry. It's not 2n factorial. It's like, this 2 is like alone. That 2 came from that 2.
So how come?
All right, then where'd you get that 2?
Yeah,
remember we said that we wanted this thing. Remember we were like, we wanted to eliminate 2 factorial from our
Right.
factorial thing, right? We wanted it to start, essentially what we wanted to do was create a factorial and eliminate 2 and 1 at the end, you know? So we had to divide everything by 2 factorial, which is 2. Questions, come on, let me hear it. I know you guys have questions.
Man, I'm wondering if we could do another problem.
So
if we have time
questions
for that.
on this problem before we move on to another problem. Mac, come on. You wanna
question.
move on already? Yeah, Frankie.
You said when you plugged in 2 for the n and it became 4 factorial over 2 factorial, how did it equal 3 times 4? Negative 3 times 4.
When I plugged in
And
into this guy, right? When I plugged in 2. Yeah, so this becomes 4 factorial over 2 factorial, right?
Mm-hmm.
So this is 4 times 3 times 2 times 1, 2 times 1, so you're left with 4 times 3.
Oh,
right?
okay.
Or 3 times 4, right?
All right, thanks.
Yeah. Anyone else?
So when we plug it into our numerator, because it's see, my thing is like, so we take what we had, right, the n plus 2 factorial over 2 factorial, and when we put it into our numerator, what was the reason again why we don't include the factorial? Is because it cancels out?
Which factorial? The 2 factorial?
Yeah, 2 factorial.
2 factorial, guys, 2 factorial is 2 times 1, which is just 2.
Okay.
So I just you can write it as 2 factorial, or you can just write it as 2. It's
okay.
They both mean the same thing.
No difference. All right.
Yep. Okay.
And then canceling it out, then it's applies to that. Yeah. I guess just picking up on that was what threw me off.
Anyone else? Ask away, please. All right. So let me kind of recap. All right. First thing we did was we derived our function a bunch of times while staying organized. Okay. We derived our function a bunch of times. We stayed organized, right? And then we just started plugging in our values into the generalized function right here, into the generalized, representation at 1. After that, we realized that there was some pattern going on with the numerator, and we figured it out. It was this guy. We then plugged that in and then canceled out with the n factorial on bottom, and then just simplified our answer to get to this guy. I'm assuming you guys want to do one more.
Yeah.
Yeah. Okay. Sure.
I feel like yeah.
Okay. I will.
Wait,
I'm gonna go down to the practice problems. These problems are on page 629. Page 629 on the PDF. It's like numbers 31 to like 40. Let me do an easier one. That one was kind of hard because of that whole like factorial trick, but the one on your final is probably not going to be that bad. What?
Can you do one the same difficulty or even harder?
You want one of the same?
Yeah, I feel like it's better if we know how to do like the hard ones first, and when we go to the easier problems, they'll be like.
So that's a very common way of thinking, but I think it's better that you guys understand the basics of it first before trying the crazier stuff. Because if you, yeah, I should have given you guys like an easier one to do. So that was on me. I'm gonna do number 31. Oh, by the way, is there like a homework due tomorrow or something, or no? Are you guys done with homework? Is there no more homework?
There's one last homework due tomorrow.
Do you guys know what number it is? Is it 8?
Yeah, it's 8.
It's 10 point.
Okay,
oh yeah, homework 8. Yeah,
so
my
homework
bad.
8 is due tomorrow. All right, I didn't know that. Okay. What was I gonna say? 31. All right, so here we go. Our function is 1 over x, and the center is 1. You guys ready?
Mm-hmm.
Yes. All right. So I mean, if you have some foresight, you're gonna see that it's gonna look very similar to the last one we did. So here we go. Once again, gonna stay organized. First derivative, second derivative, third derivative. So the first, so it's just x to the negative 1 or 1 over x, right? The first derivative is
negative x to the power of -2.
Yep. So it's going to be negative x to the negative 2. And then
negative 1 times 2 times x to the power of 2.
Right. So you guys see there it's starting to alternate. Right?
Yeah.
I'm going to do one more.
1 times 2.
And I see a factorial starting to emerge. Right? So far, so good. So watch. I'm going to plug in the center now. This is 1. This is negative 1. This is 2. This is negative 2 times 3. So, you know, I've done enough of these to kind of see like the pattern right now, right? This looks like, so once again, this is n equals 0, n equals 1, n equals 2, n equals 3. So this looks like 0 factorial. This looks like negative 1 factorial. This looks like positive 2 factorial. This looks like negative 3 factorial. Can you guys see the pattern?
Yeah, I can see where it's going. Yeah.
So I'm going to approach this one a little differently because for the sake of time, so I see that the pattern based on n, if n starts at 0, the pattern is going to look like, well, there's going to be an alternator and the first term is positive. And I see a factorial emerging, right? I see it looks like n factorial. Let me just double check, right? If I plug 0 into this, do I get that? Yeah, I do, right? I get 0 factorial with that's positive. And then if I plug in 1, do I get the next one? Do I get the next one? Do I get the next one? And yeah, it looks like it works out. So what we just figured out, once again, this piece is the numerator part of that equation. Everything else stays the same, right? So this is going to be from 0 to infinity. So the numerator part, I'm just going to plug that in, negative 1 to the n factorial. The denominator is n factorial x minus 1 to the n. And then can I simplify anything here?
Yeah, you could cancel out n factorial.
Leaving you with this guy. I should have done this one first.
Philosophy.
I actually I like the other one better.
Yeah, so you could have done it that way for this one too, but I saw the pattern, so like I just kind of plugged
No,
it
I'm
in.
not talking about the way we did it. I'm talking about like I like the other problem better.
Oh, okay. Yeah, I like the other problem too because there's more speed bumps, but that's just me. I know you guys like your roads flat, right? So.
There's a question in the chat, John.
Oh yes. How did you get x minus? Oh, well, we're
The
centered.
formula.
The center is at 1, right? That's given to us. They tell us in the beginning that the center is 1, right? So it has to be x minus 1 to the end. Anyone else? Questions on this one?
Is the n factorial in the denominator part of the formula?
Mm-hmm. That n factorial is always there.
So John, are we basically always just solving for the numerator after doing like the derivative?
That's what. So all that derivative stuff on top. That's what that is. That's the numerator.
To find the numerator. Okay.
Yeah.
And then the bottom.
You're trying to figure out the pattern of the numerator. Yep.
Okay.
Anyone else?
I don't believe it is a question. I think you can move on. Yeah.
Okay. Ooh, let me double check. Is this the one on the final? I don't think so. That would be kind of dumb, right? If I just gave you a question from the final.
You're being sarcastic.
You'll never
and then
know.
it ends up being a
You
question
always
on the
do
final,
that.
and like you just like wink, wink. That'd be kind of dumb. Wink.
No, I didn't say wink, wink this time, right?
He
I didn't say wink, wink this time.
He
so.
could be switching it up, bro. You don't know.
Okay.
Yeah.
So, wink, wink. Definitely know how to do this one. Okay. It looks like a problem on your final, right? I'm just being really nice right now. This is number 37. It's equal to 1 over x squared, and the center is 4. Man, I'm tired of all these x squared ones, man. I mean, 1 over x ones, but it's all right. Whatever. Okay, ready?
Yeah, I just realized we've done a 1 over something like this whole month. Like every time there's something new. 1 over n, like series and everything.
Yeah, they are the more interesting ones. So, all right. So here we go. Once again, same as before, right? So f of x is 1 over x squared. I like writing them like this because it helps me with the derivative part easier because I can see it better. First derivative is negative 2, x to negative 3. Second derivative is positive 2, 3x to negative 4. Third derivative is negative 2, 3, 4, x to negative 5. I'll do one more just in case. Fourth derivative is 2, 3, 4, 5, x to negative 6.
Yeah.
Now the center is at 4, so this problem, the x's aren't just going to go away because, like, you notice in the other two problems, the center was 1, and we plugged it in. It just kind of like went away almost, right? Or like we can ignore it. But since the center is 4, something else is going to happen. So watch. I plug in 4 into the original problem, and I get. How should I write this? I'm going to write this as 1 over 4 squared. Okay. I'm not going to write it as 16. Because I see that in the following derivatives, right, it's just going to be 4 cubed, 4 to the 4th, and so on and so forth. So I'm going to write it this way. Next one is negative 2 times 1 over 4 cubed. And then 2 times 3, 1 over 4 to the 4th. Anyone see it yet? Anyone see part of it yet? Maybe.
Yeah.
I'll do one more. The third derivative at 4, that is negative 2 times 3 times 4 times 1 over 4 to the 5th. So a couple things going on here that we can kind of like, I mean, I don't know. Should we do it the long way or the short way? Let's do it. Let's
like,
try.
I feel
Let's try
like
this the
it's
short way. Here we go.
yeah.
So equals 2, n equals 3, right? So if this pattern keeps on going, and it does, right? Tell me something that's going on. Tell me one thing that's happening in this pattern.
I'll first start off with like the alternator just to get it off the way.
Good. So
And then
it's definitely alternating. It starts positive, so I can just put -1 to the end. So that's one thing that's happening. Tell me something else that's happening.
the factorial is
There's
yeah,
a factorial.
I believe n
Be a little bit
n
more specific.
factorial.
There's
n
an n factorial happening, but can anyone see it?
Is the numerator n+1 factorial?
Yes, it's going to be an n+1 factorial. Why, Kim? Why is it n+1 factorial and not n factorial?
Oh, because when you plug in 1, you want it to be 1 + 1, so it's 2 factorial.
Good. So it's like, you see how there's a 1 factorial here, there's a 2 factorial here, there's a 3 factorial in the next one. So because this starts at 0, you want it to like shift up a little bit, right? So in this case, yeah, we're going to need an n+1 factorial.
And then multiplied by 1/4n.
Be careful.
To the power of n.
Be careful. It starts at 0, but the power starts at what? The power of 4 starts at?
+1 n +2.
It'll be n+1 plus factorial.
It's going to be n+2. So it's going to be 1/4 to the n+2.
It's like always look at where it starts from.
Exactly. And this is why index is so very important, okay? A lot of you just kind of ignore it, right? The index is so very important. Where you start is very, very, very important, right? Like in life, right? No, I'm just kidding. All right. So we figured out this guy. So let's plug everything in and see what cancels out, right? Anyone have any questions on how we came up with the generalized thingy?
So John, I just wanted to make sure the reason why it's n+1 factorial is because the index starts at 0.
Yes.
And it goes basically like from 1 to 2. And in order to get to 2, and the index is 1, it has to be 1 + 1 and then 2.
Yep.
Okay, and then 2 + 1, 3. All right.
Anyone else? How did you get n+2? Oh, okay. So when we plugged in our center, right? When we plugged in 4 into everything, we noticed that like these started to emerge, right? The powers are going up by 1, but the starting power was 2. So that means we need to write it so that when we plug 0 into this, it will spit out 4 squared, not 4 to the 0. Did I answer your question, Shubhan? Yes, cool, awesome. All right, so let's do this. Let's plug this all in. N is equal to 0 to infinity. This is going to be that numerator piece, right? Over n factorial x minus, what is it? 4, right? 4 to the n. So we're going to plug everything in, right? So we get -1 to the n, n+1 quantity factorial, and 1/4 to the n +2. So let's clean this up a little bit here. This becomes 0 to infinity. What's going to happen with the n+1 factorial over n factorial?
It would just be n+1.
It'd just be n+1. So I have the alternator and n+1, 1/4 to the n +2, and x minus 4 to the n. And we did it. Yay. How is this? Less bad?
Yeah, it's better.
Doable? Yeah. I think like I said, the worst part of this is just figuring out this guy. And the reason, and this thing is so important, it gets its own name. It's called the Taylor coefficient. Right? Because if you think about it, coefficient is like the number in the front, right? So it's the thing that determines the number in the front.
I have a question. You don't have to include the factorial when you're doing the summation sign when you did n+1.
I did write the factorial, right? Isn't that the factorial?
Oh, I was looking at the squared part. Never mind.
You mean I put the factorial up here too? Is that which factorial were you talking about?
I was looking at the other one. I didn't see the other one. My bad.
Okay. Any other questions? So theoretically, what this means is I can now give you guys any function I want, and you should be able to give me the series representation of it, right? Like theoretically. I use that term very loosely.
That's actually kind of crazy.
Isn't that crazy though? You guys should now be able to turn any function you want, any function in the world, using derivatives and stuff. You can now turn them into series.
Like you walk into an algebra 2 class, take a function, and just turn it into a series.
Yeah, and then like freak them all out and be like, "What?"
That's actually kind of cool.
And like I said before, this is how your calculator works, right? You can take a function, I can give you the series representation, program that into the calculator, a computer, and then it should be able to spit out value. So yeah. There are a couple minutes left. Let me give the final topics for, not like final topics, like the ending topics, like the topics on your final, okay? All right, so here we go, ready? The first set of questions are on sequences, okay? Please, it's sequences, not series. So for numbers, I won't say it, I almost said it, but for the first part, okay, do not use the ratio test, do not use divergence test, do not use the AST, LCT, whatever. Like, you're not using tests on the sequences, okay? Read the directions. It says, tell me if the sequence converges or diverges, right? Which means you have to use limits. I'll write that, use limits. Okay, and if it converges, tell me what it converges to. So meaning, if you get a number, when you do the limit, circle the number. That's your answer. Converges to that number, okay? These are supposed to be the easy ones. Supposed to be. Okay, so that's the first part. Second part, it's more like theoretical. Just know what is the difference between sequences and series. Okay, please know the difference between the two. If you don't, I'm gonna be real sad. All right, next part is geometric series. Okay, everything that we talked about geometric series, okay? So like knowing how to find the sum of a geometric series, like identifying it and justifying. Oh my gosh, that's an ugly J. My hand just spasmed out there. Identifying and justifying, right? So this is a geometric series. R, absolute value of R is less than 1, okay? If you forget your absolute value of R, I'm gonna take off half a point for principal, okay? So it's absolute value of R. Some of you were just doing R, right? I know, I'm that guy. And then the next part after that is use all the tests. Am I too old for that? Is that the rage memes? Were you guys around for that? I don't know. Use all the, no? Okay, never mind. So using all the tests, I'm gonna say, not all of them are on there, but yeah, just make sure you know how to use the tests, okay? I will tell you this, there is no telescoping series. I saw one on the review, so. Oh my gosh, I'm sorry guys, my handwriting is so bad. No telescoping series. Okay, so no telescoping series on this final. The next section is power series. So what do we do with the power series? Someone want to tell me?
Ratio test and then endpoints.
Ratio test, test your endpoints. If you still don't know what that means, or you still don't know how to deal with power series, you should definitely look into it because there's like a lot of questions on it, okay? I'll give you a hint. All three cases for the power series will appear for this on this final. All three cases will appear. So that means converges everywhere, converges at the center, converges on an interval. If you don't know what I just said, please look into it. And then the last section is the whole Maclaurin-Taylor series. For these, I'm just going to give you either a Maclaurin or a Taylor. Well, I'm going to either give you centers at 0 or centers at somewhere else, and you have to tell me the series representation of it. So pretty much the problems that we just did. It will not be as bad as that first one we did, or at least it shouldn't be. It shouldn't be as bad as that first one we did. All right. And that's it. That's the final. And then you guys are done. And then you'll never see me again. I'm good. All right. Any questions about the final?
John, are we getting the first? Wait, are we getting the whole 2-hour block for the final?
Yeah. What? I would never take away your time from you, Joanne. That'd be so much fun. Yes, you get the full 2 hours. So.
Do you think it's gonna take all 2 hours?
There are 17 questions. So if you multiply 17 times 5, that's 85 minutes. So no, I don't think it's going to take you. But some of these problems do take some time compared to the others. So I was just saying on average, if every question takes you 5 minutes, 85 minutes, meaning you're well under the 120 mark. So if you finish early, you guys can just leave, you know. Or you know, review your work, double check your answers and stuff like that, you know. So it's up to you. But yeah, this should not take. I mean, it can take. I can see if it does take you up the whole 2 hours. But I mean, honestly, it shouldn't. If you know what you're doing, it shouldn't. Any other final questions?
John, for practicing Taylor series questions, what questions do you think we should try?
I think I said it before.
Oh, it's 31 to 40? Like those?
Yeah, I would take a look at some of those.
Sure.
Yeah, on can you say that page number again?
Page 629.
All right, and lastly, I'm probably not going to be able to say this tomorrow because you guys are going to be taking the exam and some of you are going to leave earlier and whatnot, but I just want to say thank you so much to all of you for being so wonderful and being so like flexible and being so, you know, okay with like, even though like everything that's going on, you know, I think you guys are the pioneers, believe it or not. Like you guys are the pioneers of this thing, of this whole Corona learning thing, learning online. So hopefully, you know, this program helped with that, helped like kind of like get you used to like what, you know, what's going to happen in the fall, most likely. You know, your professors are going to mess up. Like your professors are going to be 20 to 30 plus years older than me, you know, and I'm okay with technology. They're not going to be okay with technology. So expect hiccups, expect things to go wrong because it most likely will. But at the same time, I know you guys are a lot more flexible than, you know, other students. So hopefully you guys, when you come across situations like this in the fall, you're going to be like, all right, it's all right. It's going to, you know, we'll get through this, you know? So yeah, if I'm not able to say it tomorrow, just good luck in the fall. College is going to fly by. I guarantee you. Like I have a hard time remembering what I did in college. I remember more high school than I do college, believe it or not. So college is going to fly by. All right. And I hope you guys take advantage of it and just have a really good time. Listen, I'm going to keep the group me open. All right. I do this with all my previous classes so that in the fall, if you're like, oh, shoot, I don't remember the difference between a series and a sequence, you know, feel free to direct message me or like message the group. You know, I've had kids in the previous years, they like message like, John, can you help me with this problem? And then like the other people respond and like it tells me that people are still there and stuff, you know. So feel free to keep that group me thing open. I'm not going to delete or anything. All right. But yeah, that's it. Good luck, guys. All right. I'll see you tomorrow. Happy studying. Ask any questions you have, and I'll see you at 8:50 tomorrow morning.
Thank you.
Thanks, John. Hey, John,
Time for the MATLAB final, guys.
one quick question.
Yeah, what's up?
You said that like you're gonna drop the lowest homework, right?
I dropped the lowest homework, the lowest quiz, and the lowest attendance quiz, I think.
Okay, thank you.
Why?
If by some
gonna
crazy, no, if by some like crazy mishap, I may or may not do tonight's homework because I'll definitely be studying for the final tomorrow.
Okay, I don't want to hear that, man. don't tell me that. Why don't you do the homework in preparation for the exam? That's like killing
No.
people.
Like I'm gonna do it. I'm just saying that how a lot of like other stuff due tonight too. So like just in case I don't get to it.
Right. So I'm lower on the priority list. I got you.
Because like that's
joke,
the
teachers
homework's due
stacking work.
homework's due tomorrow. The rest
Okay.
of stuff is due today.
Yeah, man. Learn how to prioritize better, man. That's gonna be my advice to you. But yeah,
I think the
no worries.
homework's due tomorrow,
No
like
hard
midnight
feelings.
anyway.
It's fine. Anyone else? All right, you guys can go to your next class. It's been real.
See you, John. Thanks for everything.
Yep.
Hey, John.
All right,
Have a good one,
John.
man.
Thank you,
All
John.
right, bye.
Number 850.
850. I'll be there.
All right, John. I'll see you at 6, right, for the Zoom.
Oh, yeah.
Oh yeah,
I
it's
thought
5 a.m. I forgot.
I thought you meant
forgot.
6 in the morning tomorrow. I'm
Oh,
like,
no,
we said
no, no.
8:50. Yeah. At 6.
All right.
Okay. See you, man.
See you.
Have a great day.
See you, Limerick.